Well, in our previous video, we talked about conservative fields, some physical examples, and what it meant for a field to be conservative in terms of conservation of energy, and some examples like gravitational field due to a point mass, and so on. Now, today we will start by summarizing with proof what a conservative field gives us, what benefits does it give us, and of course we will continue with our basic concern in this video, Green's theorem, which is the most important theorem in line integrals. So let us start with the following. Okay. A conservative field that is an exact differential, okay, has many useful properties which enable us to calculate line integrals in a simpler way. More easily. Okay, we will summarize those as follows. Okay, in a theorem, well, I will have the formulation not exactly in this format, but slightly different. So let us start with a D, a subset of R2, be open. Now we know what open means. It means without the boundary. Okay. Connected. Now, we defined this, I think, once, but let me repeat that. Connected means that any 2 points in D can be connected by an arc, okay, lying in D. Okay, basically it means that D does not consist of 2 separate pieces. You can always connect 2 points by an arc, and the arc lies inside D. Okay. So D will be an open, okay, connected domain. Domain or set, they mean the same thing here. Okay. Now, let P and Q be continuous in D. Now, then the following are equivalent. Okay. Firstly, the integral p dx plus q dy, I'm not specifying the path because we will say that this is path independent. In D. Okay. Now, we defined this once, but let me repeat again what path independent means. Okay. the integral, okay, is the same, okay, for all paths or curves connecting A to B, and of course, okay, lies in D. And these are, of course, okay, in D again. So it doesn't make any difference how you go from a point A to point B, but the curve is in D, and these are points from D, and the integral is the same for all such curves. It doesn't depend on the curve. Okay, so this is one property. A second property, okay, for any, or rather for all, okay, simple, closed, piecewisely smooth curves C in D, okay, one has that the integral p dx plus q dy is 0. Well, recall that we put a circle if C were closed. This just said that C is closed. And it's not an important thing. If you don't put it, but you know C is closed, it's good enough. And C, okay, f xy, that is pq, okay, is conservative. Okay. So these are all equivalent to each other. And if furthermore, okay, PQ have not only continuous, but they have continuous partials in D. Then D holds, okay. Okay, let me say, then A, B, or C, they are all equivalent, okay, implies as well D, okay, which says that Q sub X is P sub Y, okay. So basically the theorem says that A, B, C are equivalent in this case, and if P and Q have continuous partial derivatives in D, then Q sub X and P sub Y are equal. Actually, we showed this in this case. That is, if we have an exact differential, a conservative field, then if you differentiate the potential twice, it says exactly this. So that's already proven. Well, let us start with A implies B. What do they say? Well, we have a path-independent integral, and then on closed curves, it will be 0. Well, this is quite obvious. So given any such C, okay, C is closed, okay, and it has, well, because we are talking about vector integrals of vector valued functions, okay, it has some direction, okay. Now fix, okay, 2 points, A, B, and C. So say you have here A, you have here B. Now, this totality is C, okay? Call this part from A to B, okay, by a new name. So consider the following then. Let me redraw it. Okay. This is my A, this is my B, okay? Call this C1, call this C2, okay? Then, okay, by what we know, that is path independence, then by path independence, okay, integral over C1 is the same as integral over C2 because we are going from A to B, okay, in D from different paths, but we have equality by the hypotheses. But, okay, C is C1 plus from B to A, this curve, but it's exactly the negative of C2. So integral over C is integral over C1 minus integral over C2, which is 0. So this says B is correct. Okay. Now, we can easily check the opposite, that is, B implies A. Okay. But this is a little bit tricky in the following sense. It looks obvious, but it's not, and we will only partially prove it. So if on closed curves, okay, we have the integral 0, okay, then, okay, suppose then, okay, C1 and C2 are curves, okay, from A to B, okay, all lie in D. Okay, such that, okay, they don't intersect except at A and B. Okay, so the situation is the following. We have A, we have B, okay, we have some C1, and we have some C2, and they do not intersect except at A and B. Okay. But then, okay, since C, which is C2 plus minus C1, is simple, closed, and piecewisely smooth. Okay. By B, we get integral over C is 0. But this means integral over C2 minus integral over C1. So we have equality of the two integrals. Now, if the two curves intersect at a point, or 2 points, or finitely many points, by breaking it into more pieces, we can get the same result. Now, this argument also works if C1, C2 intersect at finitely many points. Okay. If we break them into smaller curves, by breaking C1, C2 into shorter curves. Of course, such that these smaller curves now don't intersect with each other except at the endpoints. But if they intersect at infinitely many points, one needs a more sophisticated argument, which is still correct, but we will omit it. Okay. So this says that A and B actually say the same thing. Now, C implies, say A. Now, what do we have here? We have a conservative field, and we want to show that we have path independence. But this is quite obvious because, say, F is PQ, and it is the gradient of phi. So, phi sub x is P, phi sub y is Q. Okay. Now then, the integral over any C connecting A to B, I will not repeat all of them here, and P dx plus Q dy, we did this before actually, is by parametrization, is A to B, we have phi sub x, x prime t dt, plus phi sub y, y prime t dt, because dx and dy become these things. And then this becomes A to B, d by dt of phi x dx plus phi y dy. This becomes the derivative of this. Or rather, let me simplify it. It just says that this is phi of x of t and y dt, which certainly means that we have phi at x of b, y of b, minus phi of x of a, y of a. Now the right-hand side is independent of C, but only depends on the endpoints, the starting point and the end point. But only depends on the endpoints. Namely, as we showed them, B point, which is phi of x of b, y of b, and A point, which is phi of x of a, y of a. So, left-hand side is path independent. So C implies A. So we get from exactness path independence. Now, if we show A implies C, we will be finished. All three will be equivalent. So what do we have? Okay, we have an open, I said that, yes, we have an open domain, and we have their path independence. Okay. Now, to show C, we need to find a potential by what we have. Well, we will do it as follows. Fix some A in D, okay, and define the potential function at xy as the integral of p dx plus q dy from A up to the point xy. Now, this is a line integral, but we didn't put a curve there because we have path independence. This does not depend on the curve, but only on the starting point and the end point. So, okay, whatever the curve, C from A to xy, okay, the value is the same. By path independence. Okay, so this is a good definition. It's well defined. Right. Now, let us calculate the derivative of phi, okay, at x0, y0. Okay. By definition, this is the limit, x going to x0, phi of x, y0, phi of x0, y0, divided by x minus x0. That's the derivative definition, the partial derivative definition. Now, what are these? This is the limit, x going to x0, of, okay, this is an integral itself, okay, and by the very definition, it's starting from A, going up to the point x, y0, okay, the inside part is the same, minus the integral from A to x0, y0, divided by x minus x0. Now, I will concentrate on the second one now. Now, here, the integral is path independent, since the integral A to x0, y0 is path independent. Okay. Let us use a special path, which will be the following. I will start from A, and I have here xy, x0, y0, okay? And I will move on C1 and then go horizontally on C2. This point will be x, y0, okay? Because y0 is the same, this is horizontal. So I will use this C. So integral A to x0, y0, okay, is the same as integral over C1 plus integral over C2. Okay. So going back to the limit x going to x0, okay, we have A to x, y0 minus, okay, I'm using this now, integral over C1, okay, plus integral over C2 divided by x minus x0. Okay. But the integral over C1 is nothing but A to x, y0. So they cancel. So this is just the limit, x going to x0, the negative integral over C2 divided by x minus x0. Okay. Now, okay, to calculate negative of integral C2, okay, parameterize C2, okay, which is actually quite easy. Y0 is fixed. We have ty0, and t runs from x to x0. So this becomes the limit x going to x0, okay, x to x0, that is, we are parameterizing C2, okay. So we have here P, we are now on C2, and therefore y is fixed and y0, okay. We have t y0 dx, x is t, okay, plus q of t y0, okay, dy is 0, okay, and that's it. And we divide by x minus x0. Now this, of course, is the limit x going to x0 of, we had, I used C2, but I have negative C2 there in front. This minus sign stays. So it is actually x0 to x, okay, p ty0 dt divided by x minus x0. Now, since the value at x equal to x0 is 0, okay, so this is nothing but the derivative of x0 to x p t y0 dt. Okay, by definition of the derivative in one variable. Well, now you integrate up to x and then you differentiate up to x, but the derivative is evaluated, of course, at x0 because x goes to x0, and this is the derivative when x is x0, which of course is by fundamental theorem of calculus, nothing but p of x0. Okay. So what did we show? The derivative of phi with respect to x is p all the time. Well, similarly, I will not prove the other part. Similarly, the derivative with respect to y of phi at x0, y0 is exactly q of x0, y0. So, okay, PQ is exact. I mean, it's conservative. Okay. So this says that we can find a potential function by using the path independence, but this, of course, is not a very practical thing. It just serves to prove the theorem. Well, finally, okay, for example, for the last part, actually, yes, for the last part, okay, if, say, now they're all equal or equivalent, okay, say we have exact differential, say C holds, so P is phi sub x, Q is phi sub y, and so P sub y is phi, we did this before actually, xy, and Q sub, Yes, of course. Q sub x would be phi yx, and these are equal because second partials are continuous. Okay. So this also holds, which finishes the theorem. Well, what does this theorem tell us, actually? It tells us that if we know that we have an exact differential, then we know a lot of things. For example, on closed curves, the integral is automatically 0. We don't have to calculate that. Okay. And we don't have to find the potential because they're all equivalent according to this theorem that we proved. Secondly, it tells us, as in the proof, that if we have path independence, well, if it's exact, that's to say, they are all the same, then we can just find another path which is simpler and evaluate it on that simpler path. We don't have to use the given path. But this will be true if we have an exact differential, that is, if the field is conservative. Well, how do we know that a field is conservative? Well, in the previous video, we talked about some examples of finding potentials directly, but this was quite work. Okay. On the other hand, if D implied conservativeness, because D is very simple. You just take Q sub x and you evaluate P sub y, you check if they're equal. Now this is very easy to check. So we have the following remark. Okay. If D, that is, Q sub x is P sub y, okay, implied that PQ is conservative, okay, then this would be a very simple way of showing conservativeness. Okay, then calculations would be quite practical. But this is not true. As this example shows. Okay. Let me give you the example. That is the following example. There are lots of them, by the way. The example is the integral y dx over x squared plus y squared minus x dy x squared plus y squared. And, okay, D is the following. Annulus. Where the radii are 1 and 3. Now this D satisfies the conditions, namely any 2 points in D can be connected by an arc. This is true. So it's connected. It's open because the boundaries, the inside and the outside circles are not included. That's also fine. Okay. But still, and of course, on D, Q sub x and P sub y are equal. Well, how? What is Q sub x? This is Q. Okay? That would be the negative of the derivative times x squared plus y squared minus x, the derivative, divided by the parenthesis squared. Now, P sub y this is P, okay, would be derivative of y, x squared plus y squared, minus y times the derivative of the bottom part, the parenthesis squared. Now, clearly, you have here y squared minus x squared with a minus sign. So it's x squared minus y squared. And this is clearly x squared minus y squared. So they are equal on D. Okay. So q sub x and p sub y are equal. That's nice. But we don't have exactness here. There's no potential function. Why? Okay. If it were exact, then, for example, on closed curves, we would have 0. Let us check. Where C, okay, is this one. Counterclockwise oriented circle. Of course, it is indeed. Okay. D was the annulus, and indeed it is so. And very easily we can parameterize. Okay, namely, C can be written as, okay, it's a circle with radius 2. So it's 2 cosine t, 2 sine t, and t goes from 0 to 2 pi. So this integral is 0 to 2 pi. Now let us substitute the values. We have y over x squared plus y squared. So y is 2 sine t divided by x squared plus y squared, which is 4 sine squared plus 4 cosine squared. So it is 4. And the x is minus sine t plus the other one actually minus x dy, so it's 2 cosine t, and y is sine t, so it's 2 cosine t again, divided by, okay, the sum of the squares, dt. Well, obviously enough, okay. Wait a minute, we have the derivative contains another 2 here. So 4's cancel out. We have minus sine square and minus cosine square, which is minus 1. So it's negative 2. Very simply. But then, okay, so in the theorem, B of theorem does not hold. But A, B, C were equivalent. So, okay, C is not true. C is also not true. Okay. Well, conclusion. Okay. Q sub x equal to P sub y does not imply that we have a conservative field. Well, this is quite disappointing because if it were true, we would know conservativeness just by checking this equality, and it will be very easy. Okay. Well, why did this happen? Okay, this is contrary to our common sense, of course, but the problem can be seen in the following. Okay. On this annulus, between the two circles with radii 1 and 3, okay, the function is nice. It has partial derivatives because 0, 0 is not included. Okay, the only problem is at 0, 0. If we take it out, it's not in D now, okay, then everything happens to be all right. These are equal, they exist, but one bad point inside the curve makes everything go sour. That is, this is not true. Now, to make this more rigorous, okay, we will next prove Green's theorem, and we will check its conditions here. So let me state and prove Green's theorem, which is the basic theorem of this section. Okay. Now, Green's theorem, in detail, has the following hypotheses. Let us start with D. Okay. Let right, D be an open, connected domain in R2. Okay. P and Q be continuously differentiable functions, okay, on D. And let C be a closed, simple, piecewisely smooth, and counterclockwise oriented curve, okay, in D, but it will have another property such that, okay, the region it bounds is also in D. So the problem with the previous example will not occur here. Namely, okay, together with, C is such a curve that its inside is also in D. In the previous one, there was a hole inside. There was a smaller circle of radius 1 inside the region bounded by C, but it was not in D. But here we exclude that. Okay. Then one has the following: the integral over C of P dx plus Q dy we stated this result before, is the double integral over R of q sub x minus p sub y df. Okay. Now, if the inside part of C, okay, is also in D, it means that P and Q have continuous partials inside as well. If that's the case, then Q sub x and P sub y are equal, says that the integral over the closed curve is 0. So B holds in the theorem, which means equivalently that it's path independent, but we don't need that here, that it is conservative. So from here, what we want will follow. We will not be able to prove this theorem. It's quite a deep theorem in this sense, but we will just show the proof in a special case. Namely, this will give you a taste of why a double integral and a line integral are equal in the first place. Okay. So we will set up the following. Okay. We will consider a region which is, well, this is C, of course. It's a closed curve. Everything is in D. I will not write that. But C has the following specialty. The region it contains is a simple region for a double integral in both directions. So the special case is that assume R is simple with respect to x and y, both. So we have such a thing. Okay. Now, let us put some more notation in here. Okay. Say we have the top and bottom points here, say A and B, doesn't matter. We have these points, okay. The total is C, okay, let me change this notation. I don't want to repeat this 2 times. So let me calculate this as C1 and C2. And of course, C is C1 minus C2. Okay. Because of the direction problem. Okay. Now, let us take the part. Well, maybe I should also give some more notation here. Now, this curve, because it's a simple region, is x equal to g of y. And this one is x equal to, say, h of y. Okay. Because it's simple, then we get 2 such curves. Okay. Now let us consider q sub x dx, dy, so dA. Okay. Now, because this is a simple region, I can write it with respect to x first. So this would be in iterated form, okay, q sub x dx dy. Now x will change from h of y to g of y, and y will change between a and b. This is because R is simple with respect to x first. Of course, in q sub x, I have x's and y's. Okay. Now, let me look at the first integral more carefully. Okay. Remember, q sub x is the derivative of qxy when y is constant. This means that, okay, we can regard it, because y is constant in this first integral, it's a function of x alone. And you differentiate, and then you integrate. So what does all this say? Well, here, okay, thinking q sub x, xy, as derivative of g of xy, okay, as derivative, okay, let me say as the derivative, where y is constant, in a partial derivative, y is constant, and gxy, or gx, is qxy. Okay. This says that we have derivative of g and integral of g between 2 points. So it is, so the integral is, okay, g of, instead of x, you take derivative and then integral. So, well, I have, sorry, too many g's. They are confused. So let me put here k of x. So I have at the end then k of the upper one minus k of the lower one. Okay. But this is nothing but, okay, q of, now I'm putting these instead of x's, okay, but y's are y's, minus q of h of y, y. So, rewriting, this then becomes a to b of q of g of y, y, minus q of h of y, y, dy. Okay, I used here the fundamental theorem of calculus. Integral of the derivative is the function itself. But y is constant. I'm only working on x so far. Now, let this stay there. Let us consider now, okay, the integral over c of q dy. I mean, the second part of the line integral. Now, certainly, this is the integral over c1 plus integral over c2, and we can parameterize each of them separately. For example, c1 can be parameterized very simply. I said, yes, minus c2, of course. I wrote it over there. So, if we parameterize c1, okay, in it, certainly y is the parameter. So, it is g of y, y, and y changed from a to b. Okay, the direction is still correct, because when y increases, we go up. So we move in the correct direction for c1. For c2, actually for, right, minus c2, well, in this case, the x values are h of y, y, these are x's, and y change in the opposite direction. So a to b again. Now, using this parameterization in both integrals, for the first integral, okay, I have q of g of y, y, q of x, y, okay, and dy. and y changed from A to B. Well, on minus C2, I have plus let me see. I put C1, C2 in this direction, so C is C1 minus C2. So this is the correct one. So that is, I should have, I have some problem here. I will correct that in a minute. This is h of y, okay, and dy from A to B. See if I got the correct thing. I should have a minus sign here. Why is that so? I have C is, well, of course, this is wrong. It should be plus. I have the direction correct. So here, this is so. So this is the integral over minus C2. Okay. So I should have a minus sign. Okay. Now this says that, looking at the two, so because these two are the same exactly, okay, it says that integral over r 2 sub x dA is the same as integral over c of q dy. I will not prove the other part, but similarly, okay, integral over r minus py dA happens to be p dx. Okay. So this finishes the proof. In the case of region R, which is simple with respect to both x and y's. Well, if you can split the region R into finitely many simple regions, which are simple with respect to both x and y at the same time, then this proof works. You just repeat. But if you cannot, of course there are such regions, if it's more complicated, this argument will not work.